אז מיוט.
אפשר רק להוריד את הסאונד הזה בבקשה. בסדר. אנחנו מתקים את זה, כן? את זה אני מודה לסך. כן. יותר טוב? לא? אפשר ללכת להגדרת שלנו.
זה לא ידע את CMI.
יציאת סם. ואנחנו נתחיל את הבית. מה קורה?
בסדר. אז אני יכול לקחת אותו ב-12 רבע.
בסדר, אני חושב שאני מדבר אבל שיש זמן 12:30 צריכה להיות, אז אני אולי תחזור שם, ואז אתה נסיים, אז אתה חשוב למטה בננה.
אוקיי, אז פשוט הוא ילך
או שיכול לבוא שיש הצלחה במשרד? זה רק אותם נמוכים.
שמה?
Recording in progress.
של הרואה, קרוב לפרומן,
יש שם את לב הזהב.
כן.
יש את לב הזהב שיותר קרוב. זה לב הזהב.
אתם על מיוט.
אמרנו זה בערך 45 דקות באנגלית.
אני חושב שיש אנשים שאמורים להיות פה עדיין לא יודעים.
חדר קפה.
כן.
תודה. היי.
זה היה אמילי. Okay, let's start. So, hi everyone. Here. I can see. So it's my pleasure to introduce our speaker today, who is Gil Markovich from the Chemistry Department at Tel Aviv University. Gil did his PhD under the supervision of O.H. Sosnovsky in Tel Aviv and finished in '96, where he continued to a postdoc in UCLA with Jim Heath. And since, and then he returned. 98 he returned actually.
Yeah, 98.
Right. And 98 returned to Tel Aviv and opened his lab. And that's about 2 years later is when I met him. When one of his research topics was working on magnetic properties of nanoparticles, and we were studying the wave transition using the STM. And since then, he's an expert also on magnetic properties of nanoparticles, on preparation of these colloidal nanoparticles and studying their physical properties, ferroelectric effect in particles, and recently, or actually quite for a while, also chiral-optical effects in chiral particles. And today he's going to talk about the formation of chiral symmetry in nanocrystals. Gil, the stage is yours.
Thank you very much, Amos. It's a pleasure to be here. As Amos mentioned, most of my recent interest in science is about combination of chirality and inorganic nanostructures, nanoparticles, nanocrystals in different ways, and optical properties. And actually this talk will have a lot of chemistry, so pardon my chemistry. I will try to explain everything, all the concepts, but please interrupt me if something is unclear, or if you have questions also, I'll be happy to answer during the talk. So my group basically works on nanocrystals made by wet chemical methods, most of them. And here also chirality goes into the play. So what is chirality? It appears also in physics, we just discussed, in condensed matter physics and particle physics. So chirality is basically the absence of mirror symmetry, right? It starts with the hands, where right hand and left hand, which are mirror images, are not superimposable. So in chemistry, it goes to this kind of chiral molecules. These are typical amino acids. We have a carbon atom, which is bound to 4 different chemical entities. And this also breaks the mirror symmetry. So right-handed and left-handed amino acids, most of the amino acids except one, are chiral. A lot of biomolecules, many molecules associated with life, sugars, some lipids, nucleic acids, of the building blocks of DNA, all chiral. And this is actually an important thing because they allow this complexity of the biochemical processes. And also macroscopic objects of living systems can be chiral due to some intrinsic microscopic effects that are actually not well understood. Actually chirality, through the work of Louis Pasteur, for example, and others, was recognized to be associated also with effects, chiral-optical effects or optical rotation. So chiral objects, when they are very small, like molecules. Yes?
Is it a temperature-dependent phenomena? Maybe about a certain temperature of chemical bonds can switch?
Yes, this is a very good question, actually. So, okay, the 2 mirror images in the chemical language, they are called enantiomers. And some molecules, they have different energy barriers for flipping bond angles or directions. So Yes, so each molecule specifically might at some temperature reverse its structure to the other enantiomer. It's called racemization also. A racemic mixture is an equal amount of right-handed and left-handed objects. So yes, this might happen. Some molecules do it at room temperature, and some of them will sustain a lot of the pharmaceutical molecules that we use. They are chiral, and one of the criteria to have a stable pharmaceutical is that you have a relatively large energy barrier to flip this direction. So Louis Pasteur actually is the one that connected optical activity. It was known from like 50 years before Pasteur, beginning of 19th century, that quartz, for example, quartz crystals, which are also chiral, this will be the major topic of the talk. So they can rotate the polarization of light passing through the crystals. The Arago was the first that observed it. And then it was observed also for molecules like tartaric acid or tartaric acid salt. The tartaric acid is a natural acid appearing in wine, for example. So it was known that tartaric acid crystals can rotate the light. And it can also racemize actually under certain conditions of pH, of acidity. So tartaric acid can invert or racemize. So Pasteur took a solution of racemic salt of tartaric acid and he crystallized them. And it turns out that this material will crystallize separate, the molecules will crystallize separately, the right-handed and left-handed one, which actually is the minority of chiral molecules. Most molecules would like to actually join together, the two enantiomers. So in this case, it could recognize that how the facets of the macroscopic crystals, it could observe them by eye, they were organized in some asymmetric fashion. So it could basically distinguish between the two types of crystals, right-handed and left-handed. So while the racemic mixture that he had did not rotate the polarization of light because it was 50-50, when he dissolved each separate group of crystals, right-handed and left-handed, then he saw these opposite rotations. So he understood that basically the two groups of molecules that are basically the same material, but has a different property. So he realized that there has to be some mirror symmetry between the two groups. So we had the idea of actually exploring this phenomena on the nanoscale. So in the nanoscale, you cannot take crystals and separate them by tweezers, individual ones, and say this is right-handed, left-handed. So we need some other way to try to separate them or to control whether we make right-handed or left-handed crystals. And we are talking not about tartaric acid, which is an organic compound, but inorganic compound, like quartz. Okay, so this is like model of right-handed and left-handed quartz. Sand, right? So if you go, you take sand grains, so 50% of them will rotate light to the right or to the left. So quartz is like the most famous mineral, inorganic material that is chiral. Chiral, it means that there are certain, that's my next slide. Oh, okay, later slide. But quartz is one of the, it has a symmetry, which is a screw, it has a screw axis where you have helical order of the atoms in the material that give you this, right? Because a helix is basically the most maybe trivial chiral object that you can think about. Why is symmetry? Okay, so what I will tell you about is actually symmetry breaking. So can we control how many right-handed to left-handed objects like quartz crystals, for example, we make and maybe can control by chemical means when we prepare them. It's not a trivial thing, right? To cause basically similar or the same material to form or same crystals to form, but to have a preference for one-handedness, okay? One type of direction of the helix is one-handedness, it's called handedness. So how do you do that? And why is it important? So I already mentioned pharmaceuticals. There was the famous case of thalidomide in the 50s, mostly in Germany, in Europe, also in the US. A medicine that was tried on for different conditions. One of them was morning sickness in pregnant women. And it turned out that one enantiomer indeed was helping this kind of situation, but the other enantiomer was causing birth defect, very severe birth defect, because it was influencing the DNA, getting into the DNA and causing mutations. And actually, this molecule is an example for what you asked about. Actually, it racemizes very easily at room temperature. So even if you could separate one enantiomer, which at that time they were not aware of that, but if they could, it would very quickly racemize and form the other enantiomer in an equal quantity. So of course, as they realized that this is the problem, they stopped using this medicine, at least for pregnant women, for other things. And since then, all the pharmaceutical industry became very careful about this kind of chemistry and selecting the right enantiomer for the treatment that you need it for. So one of the curious things, for example, just to explain to you the importance of enantiomer. So this is a curiosity. So a molecule called limonene, for example. So you have it in the peel of lemons and oranges. And actually, it's the same molecule, but opposite enantiomers in lemon and orange. So the scent of lemon and orange that you can definitely distinguish is just the same molecule, but the other mirror image. They give you the two smells. So it tells you also about the specificity of your sense of smell. So associated with that is the riddle of homochirality, the origin of life. In all living creatures, basically, and plants, so you have only one mirror image except for this kind of curiosity, almost like 99.9% of the biomolecules, they are just single mirror image. So all the amino acids are basically called L, they are left-handed. All sugars in living systems, they are D, that's right-handed. So this is a mystery, right? How symmetry was broken at those early times when the first cells or living systems started appearing. And there's a lot of work, or there has been, and also still, a lot of work to try to come up with models, how this symmetry breaking occurred. And of course, this will be a key ingredient in the understanding how life came to be. So, and in our case, also, the other motivation that we have is that we think that actually looking at the symmetry breaking in the formation of chiral crystals, the problem of nucleation and growth in general of crystals, if we could look at it specifically in chiral crystals and try to understand how the most primary nucleus of a crystal decides whether it's going to be left-handed or right-handed, will be a key question in the understanding of crystallization phenomena in general. Sure.
Just before I go to crystals, you just mentioned that the limonene is a molecule that appears once as right-handed, once left-handed in nature. So that means that there are other molecules, or this is
probably yes. I'm not an expert on that, but they are very rare. Those are very, very rare examples, and they are not like key ingredients in like general building blocks of our body. Those are appearing, I think, in very, very special circumstances, but they appear. I'm not sure, exactly how many are there, but they are really rare examples. But proteins, DNA, all this, they are like single-handed.
Question?
Yes.
So, for example, in this orange versus the lemon example, in the orange, you have only one chirality, and in the lemon you have only the other, or is it like a mixture where you have like
that's a good question. I don't know exactly. I guess, yes. Remember that even in the peel itself, the aromatic oils that you have in the peel, it's just part of it is this molecule. So, you know, it's a mixture of a lot of molecules that if you will smell only this pure compound, you might not associate it with orange or lemon because it gives you just part of the scent.
No, but
so, but I cannot tell you. Yeah, probably. I guess that yes, but I don't know if it's like single enantiomer in each, or if you have a mixture with just a majority. The word for having, when you have a mixture of two enantiomers and it's not exactly racemic 50-50, we use what is called enantiomeric excess. So, okay, so if you have like 80 and 20%, so it's an enantiomeric excess of 60% to one side, okay?
But somehow the orange knows how to grow only.
Yes, it's you know, complicated chemical processes. It's, I think, starts from terpene chemistry, which is one of the cycles in the body that does that where a lot of molecules are involved in the production, and it's like more relatively hydrophobic molecules. They are dissolved in oil.
Can I ask you?
Sure.
So maybe I'm missing something. Maybe this is a question. On the orange and yellow lemon, I see the symmetry, and it's related to the right versus the left. It's very clear. But on the top, the two molecules, the axis.
Yeah, it's a special kind of symmetry. It's not like a carbon, like the normal what I showed in the beginning in the amino acid, where you have a carbon bound to 4 different groups, but there's a twist in the molecule maybe, and so yeah, it's the combination, the relation between.
On the top one, it's on the axis. The way I see it, the N, is that correct? No,
this bond brings this part out of the plane.
That is more or less clear, but the other one, no.
This one, yeah.
Is it? No,
on the top of the page.
The thalidomide.
Thalidomide, okay.
Because they look identical except for the strength of the bond in the middle.
So yes, the bond in the middle tells you if it's like this or like this. So, okay. Sorry, yeah, it's this kind of chemical conventions of drawing. So it comes out of the plane this way or this way, and this gives you the broken symmetry. Yes, sorry.
You might want to open the chat. Especially in the chat box.
No, it's not answer, it's just writing there.
Yeah, no, I will not have time to.
Yeah, but you can, on the more you can do hide the thing.
Right.
Yeah.
Hide. A floating wing, yeah, okay.
Yeah. So crystallography. So you have like 230 crystallographic space groups that, you know, you categorize all known crystals, you know, not including quasi-crystals and that stuff. So out of them, 65 space groups can host chiral structures. Out of them, like 22, which are like 11 pairs, this is the category where quartz lies. So those are really chiral space groups. So they have this helical motif, either 3-fold or 4-fold or 6-fold rotate screw axis. In quartz, it's 3-fold screw axis. And there are other very low symmetry groups where most proteins and other chiral biomolecules crystallize. They're just so low symmetry, so they must have some chiral asymmetric structure in the unit cell to really build this kind of. So they are also chiral. Very prominent mineral or inorganic material that has been actually the only material that has been studied, inorganic material that has been studying for its chirality is this salt, sodium chlorate, which gives you basically chiral arrangement of these building blocks, sodium ions and chlorate ions in the unit cells. So how can we break the symmetry and obtain an excess, an enantiomeric excess in quartz or sodium chlorate or whatever crystals that we use? So can we somehow spontaneously break the symmetry? Like maybe how life started? So you will need some, I mean, one possible model will be to have a small fluctuation in the more or less equal amounts of the two enantiomers or nuclei of crystals that are forming. And then you will need some sort of positive feedback that will cause some very strong amplification of this small random thing. And as I told you, in sodium chloride, it has been studied some years ago, and people observe this kind of effects and try to understand really building models and experimentally also how the symmetry breaking occurs, for example, in this sodium chloride, where it's possible to have random breaking of the symmetry and evolution of the system to give you crystals of only one type, one-handedness. And you can also think, and this is what we started doing, maybe we can have an external influence, like if we drop some chiral molecules that will interact with the building blocks of the crystal, can we cause this crystal to break the symmetry by this external interference? And this is what we have been doing. So we take achiral crystal precursors like ions or atoms that will be the crystal, like quartz, like silicon and oxygen, for example, and maybe bring an external interference. Yeah.
When you talk about symmetry breaking, you assume that the energy of the two states is the same.
Yes, so right, it's basically the same material, but it's a very good question. I mean, for example, there's like in physics, people study the weak force, which is supposed to actually break the symmetry, that should give you different energies, but those energies are so many orders of magnitude lower than KT, for example, at room temperature, that it's very hard to imagine how it will affect the breaking of the symmetry. But people have suggested that this might be, for example, this kind of tiny energy difference might be the cause. But I mean, I don't think there's a good model how it will occur. Even they discussed collective effects, but I don't believe it.
As far as I recall, most of the biological molecules will be right-handed.
Yes.
Is that true for most crystals as well?
No, it's a minority, but still there's a lot of, that's a good question, but yeah, there's a lot of inorganic, you can find in tables lots and lots of inorganic minerals, materials that crystallize in chiral spacebook, but it's still the minority. It's a loud minority, good definition.
But if you grow these crystals, typically they grow in polycrystalline fashion?
That's very, okay, how the crystals grow and what they form depends a lot on the way they form. We work in solutions, so I mean, we don't work, for example, in a melt that crystallizes into a solid, but in a solution where you go in concentration to supersaturation and let them form. And
for you, it's nanocrystals.
For me, it's nanocrystals, they are colloidal. We like them to stay in the solution to be stable. So we need some charging if it's in water or something like that, that will help them to be at least metastable in that sense, that they will be trying to make them uniform, small size. And there are many advantages to studying this kind of colloidal dispersion. I will explain in a minute also why.
But each one of them has one parameter.
Each one of them is a single crystal. If it's a single crystal, it's a single chirality. That's a very good point. And because in some growth conditions, you can have defects. For example, a twin defect is a defect in a crystal that when the crystal starts growing in the mirror image of itself. So this is bad. I mean, we want them to be single crystals and ideally to count how many right-handed and how many left-handed there are, but this is tough. So I was talking about breaking the symmetry. Let's say this represents quartz or whatever, this helical structure. So breaking the symmetry by some external interference. This is tartaric acid, for example, and see what happens. So back to the sodium chlorate. So Kontipudi, this was a very significant work from 1990. What he did here, he had supersaturated solution of sodium chlorate. Sodium chlorate is a salt that is very soluble in water. So you need very high concentrations to get it to crystallize. And you you can do it statically, just have a plate, let water evaporate until you get too high concentration where you cannot have dissolved salt anymore and it starts crystallizing. in that case, it will form this kind of statistic. This is an enantiomeric excess of the sodium chloride. What they do is they grow the crystals, they go to a microscope and see which direction each of them rotates the polarization of light. So they really count them one by one, because they're relatively large crystals, I don't know, millimeter size or something like that. And then they count and they see that basically they get a racemate. This is just by static conditions, but when they steer the solution and let the crystals go under steering, you can get the system to full enantiomeric selection randomly, one time right-handed, one time all of them left-handed. Interesting, right? A way to break the symmetry. Here, what they think is what is called secondary nucleation. So the rate of formation of crystal is very slow. So let's say initially you get maybe one seed. This seed can act as parent for additional seeds or to grow on top of it, maybe. This is what secondary nucleation means. In the same handedness as the parent crystal, and this steering might get you a shear force that will disconnect this one, grow, act also as a parent, and so on. So big amplification of this asymmetry in the system, which brings you the whole system to the right or to the left. Actually, it might be much more complicated than that. And actually, this elusive secondary nucleation is something that we are trying to really follow and understand what does it mean exactly. But this kind of symmetry breaking is
the direction of studying is not important there.
No. There were other experiments where people claimed the direction of steering could be, or in other, not really steering, but some shear force, strong shear forces. People claim that they see the symmetry breaking affected by the direction. This is still controversial, but there were claims that things like that also. This is another by Cristobal Viedma, more recent work, and others. Another case. You take already grown sodium chloride crystals that are racemate. So that's 50-50 right-handed, left-handed. You start steering them very hard in water. And over time, you see that they evolve to completely go to the right of or the left. So because it's very soluble salt, so it can also dissolve and recrystallize, So it's kind of recycling of the material. And by this, you can also break the symmetry, called Viedma ripening. So you ripen the crystals, you let them evolve, and you can get also to enantioselection, which is random, a very interesting phenomenon that people are still studying. But let's go, okay, I'm taking a lot longer time for the introduction, so I must progress faster. So as I told you, we distinguish between right and left-handed crystals by polarization of the light passing, changes in the polarization of light. So you can have optical rotation, that is light passing, and linearly polarized light can rotate left or right, depending on the enantiomer you have. I will go fast. So the other possibility is look, actually, this optical rotation usually you do at wavelengths that are not absorbed by the material, but you can go also, for example, in biomolecules like proteins to around 200 nanometers into the UV. And there you have absorption of the amino acid, the peptides that form the proteins. And you have a phenomenon called circular dichroism, which is the difference in absorption between left and right-handed circularly polarized light, which happens in any chiral molecule because of the asymmetry of the orbital in the molecule. And from this this is actually more conventional to use to characterize chirality, or like in biochemical systems. And you can characterize it by the symmetry factor, it's called G, which is the difference in absorption coefficient between the two circular polarizations divided by the total absorption. This gives you an estimate of how strong is the optical activity or the asymmetry in the interaction with light of this chiral system. Usually in chiral molecules, it's a very small effect, 10 to the minus 3 to 10 to the minus 4. So it's a small optical effect, but measurable, and many biochemists use it to figure out configurations of biomolecules, because the this spectrum basically that you make is very sensitive to the bond angles in the molecules. So you can follow changes in the angles in the protein when the conformation of the protein is changing and so on. There are other optical effects. I will hopefully get to tell you about a system where you look at circularly polarized light in the emission of the nanocrystals that we are after. So the first system that we studied, it was an idea of a former very talented and brilliant PhD student, Asaf Ben Moshe. He said we were working on all kinds of, I will not give you the whole story, but we're working on chirality or interaction of achiral nanocrystals with chiral molecules. And he said, why not look for intrinsically chiral crystals like quartz and see what happens? So he started with a semiconductor called mercury sulfide, or it's a mineral actually from which mercury is extracted in nature. It's called cinnabar. It's actually a red pigment. It was used as a red pigment for a long time until they decided that mercury is poisonous. So for this, he took a small biomolecule called penicillamine, which is very similar to the amino acid cysteine. It has this sulfur here, which should bind strongly to the mercury. So we thought it will affect the way the nanocrystals of mercury sulfide will form and hopefully break the symmetry. So he could make it very simple preparation of taking mercury ions and sulfide ions and let them form the nanocrystals in water in the presence of penicillamine, either a left-handed or right-handed version of penicillamine. And indeed, it could get, this is circular dichroism spectrum of these nanocrystals, it could get very strong circular dichroism, which already meant that probably he broke the symmetry and there was an excess of one time right-handed and the other time left-handed, depending which penicillamine interference you put into the solution. And then we tried, and there was, you see, the symmetry factor here is 10 to the -2. It's much better than chiral molecules because here you have already 10 nanometer big nanocrystal with a lot of chirality inside because many helices of mercury and sulfur. So it's more optically active. And for example, what we could do is change, actually not take just pure L or D penicillamine, but mixtures at different enantiomeric excess of this external interference and see what happens to the magnitude of the circular dichroism in the mercury sulfide. And you get something that is roughly linear or even sublinear. So at this point where you take just pure L or D penicillamine, you get some sort of optical activity. So you can say, okay, I know that there's a large enantiomeric excess, but you cannot count. By electron microscopy, you cannot tell right from left because you get just a two-dimensional projection of the nanocrystal. So you cannot say which is left, which is right. So we knew we have a large excess. Today we know that it was about 75–80% from other work of some Japanese group, but that was a challenge. And I don't have much time, so I will. We also have nanostructures of tellurium and selenium, the two elements. They also crystallize in the same space group as quartz and mercury sulfide. And we could grow, Asaf could grow nanostructures of these materials and also show very interesting optical activity effects and chiral shapes of the nanocrystals. But I don't want to get into that. But
you started a bit late.
Okay, no, but I still have a lot to tell you. So it's still an introduction. Now what we go so this is the end of the introduction. So we had a few chiral materials that we know that by using strongly binding chiral molecules that have, for example, sulfur atoms that can bind strongly to either mercury sulfide or tellurium or selenium, you can really break the symmetry. In each of them, okay, we got very interesting also chiroptical effect and so on, but we didn't have a way to really count how many right-handed and left-handed nanocrystals we have. We just knew that we have some difference. So we have this kind of curves. When we look how the optical activity of the nanocrystals depends on the enantiomeric excess of the chiral interference that we put. But we didn't know how much we have. So that was the challenge. Can we, do the Pasteur experiment and really count? So then came a new PhD student, Uri Hananel, who just graduated and now postdoc in NYU. And we said, okay, there are these tables, as we said, it's a large minority. So there are many crystals that are chiral. Let's take something completely different. So there are lots of salts of lanthanides, right? Lanthanides are rare earth mineral. So they have very specific chemistry. All of them form like trivalent ions in solution. So we took this model system called terbium phosphate, or it's actually also minerals that you can find in nature called rhabdophanes. And we doped them with a little bit of europium, which is interchangeable with terbium very easily because they have a similar chemistry. I will explain in a minute why. And also crystallized, same space group as quartz and the other materials that we have been working with. And these guys, we said, okay, here the chemistry is different. We will try actually tartaric acid because we know that it has nice interaction with these lanthanide ions in solution. So we said we'll try that as the external chiral interference. And you can find this, you can make this fairly easily, these needle-shaped nanocrystals. Again, each of them is a single crystal with well-defined endedness, hopefully. And let's study that. So initially we do it just in boiling water, 100 degrees centigrade, put again, terbium, phosphate, also a little bit of europium, like 95% terbium, 5% europium, boiling water, tartaric acid, and make the nanocrystal. So the idea here is that we are going to probe the chirality or the statistic in the system, the enantiomeric excess, by looking at the circular polarization in the emission. We chose that because we knew that europium ions that we put in the nanocrystals, when they are in chiral environments, they give you very strong anisotropy in the circularly polarized emission that they give. Here it's not 10 to the minus 3, 10 to the minus 4, it can be 10 to the minus 1. So it should be very easy to detect. So europium is a very good reporter of chirality. And the idea was to excite terbium in UV light, and it passes the energy to the europium, and this guy emits. And there are many advantages for that. I will not go into all the advantages that there are, but it turned out also, as you will see, a very interesting and comfortable system to work with. And we've built a spectrometer that is designed to measure this difference in circular polarization in the emission very sensitively. And okay, we started doing the synthesis in the presence of tartaric acid, and we see, okay, so the lanthanides like europium here, they have a well-defined series of lines in the visible near IR spectrum. That's also one of the advantages where you have a very easy fingerprint to follow. And you can see that taking tartaric acid left or right give you strong difference. This delta I is the difference between the two circular polarization components that are emitted. So you can see we flip them and it's a very nice, good signal to noise. Clearly, tartaric acid does affect, and you can get an enantiomeric excess due to the presence of tartaric acid. And actually, okay, and when you take a racemate of tartaric acid, you get 0. So this is fine. Then we said, tartaric acid works, let's try similar molecules. Okay, I will not go into the chemistry, but those are similar molecules with similar chemical groups that are also chiral. And we saw that indeed tartaric acid was a good choice. It gave us a lot of signal. Actually, one of the molecules called camphoric acid gave us 0. So it's chiral interference, but no effect in spite of having similar chemistry. So it was clear that the molecular details are very important. Also a glutamic acid, which is the amino acid that is also chiral with similar chemistry, gave very little effect. So good, tartaric acid is good, we said, and we started exploring further. So here we look at the optical activity as a function of the enantiomeric excess of tartaric acid. And bang, this is what I was looking for, a system that will not give you a linear or sublinear dependence, but will saturate. So here, already at some moderate excess of about 40% or so, or 50%. 50% excess means 75%, 25% of the two tartaric acid types, the mixture, still already gives you a saturation in the optical activity. So we thought that, this is a hint that in this system you get some kind of nonlinear amplification, and you get like full selection of the enantiomers in the crystal. So this is a good system. So this is our assumption. And you can see also that glutamic acid, which is a bad chirality director, doesn't give you this kind of saturation. Give you this, again, this sublinear, very weak effect. So that was like a temporary conclusion that we had, but we couldn't really prove it. Again, we couldn't count the nanocrystals. But now I'll show you a way where we could count nanocrystals. And this is a collaboration with a former PhD advisor, actually, Ori Chishnovsky, who does a lot of microspectroscopy experiments. So spectroscopy under a microscope. So here, because we are looking at emission from the nanocrystals, emission is a more sensitive measure than absorption, like in circular dichroism. So with emission, we could come with an optical microscope. I look at isolated nanocrystals and really try to start counting them. It was more complicated than that, because with the optical microscope, you cannot see really the nanocrystals. The resolution is not good enough. They are nanometric. They have a width of maybe 40 nanometers and length of half a micron. So it's really borderline for optical microscopy. So we had to go first to a transmission electron microscope, identify the position of isolated particles, mark the coordinates, go to the optical microscope, and measure the circularly polarized luminescence from this nanostructure. And here you see how, again, this is like the emission spectrum looks like. And this is like comparing right-handed and left-handed circular polarization coming from a single nanocrystal. This is by playing with the polarization filtration. So you can see that at certain positions, especially this weak line here at 651 nanometers, you have a big difference also here and here. So my student Uri and Eitam, Uri's student, they sort out, they decided they are going to, it's very fashionable, right? Use a machine learning algorithm to actually sort out, you see the spectra are very noisy. At 651, you can really see that there's some from L and D crystals, clear distinction, and some other places. So they say we will just take different intensity ratios in the spectra and analyze them and optimize them, and using a machine learning algorithm, train it to identify left-handed and right-handed nanocrystals. So actually it worked. So this is like the result. So you have different ratios of intensities, and you can decide on different ratios to, as features or dimensions in the space that the machine learning algorithm is trying to optimize. And indeed, you can see that all the red and blue dots are appearing in different spaces in this parameter space, meaning you can really distinguish, actually with certainty of about 99.something%, which is left and which is right. And actually there was only one mistake here, but after looking carefully, it wasn't really a mistake of the machine learning algorithm or the noise in the spectra, but it was, first of all, it showed that the synthesis really produced. Those are two samples from two different syntheses with pure tartaric acid, L and D. So really, tartaric acid does direct the system to 99% enantiomeric purity, except in one of the syntheses, in the red dot synthesis, there was one particle that was the other end. So we find an interesting system that knows that we can, by this external interference with tartaric acid, cause it to go all the way to the right or to the left. So we can take these are TEM images of the nanocrystals, and now go with the optical microscope and do, label them blue or red, left or right, and say which one is right and which one is left. So actually, this is what I call a nanoscale version of what Pasteur did, right? We can count. So this is very useful. Hopefully, will be very useful for other things we want to do. So back to our system. So we have this, right? We found that we can really go all the way to the right and to the left in this terbium phosphate system when we use tartaric acid as an external chiral interference. So then we started exploring this further. So, okay, here you see the results that we already had. What you see here, H, is basically the difference in the enantiomeric excess of the tartaric acid. And we use H because it's like, we call it like effective magnetic field. You see those look like magnetization curves. And when we go down in the temperature of the synthesis, you can see that the magnetization curves are starting to get steeper and steeper around 0. So at 40 degrees, actually what you see is that when you take a racemic mixture of tartaric acid, you get all over the place. So you have a random symmetry breaking in the absence of a clear difference between right and left ended tartaric acid. Actually, we found that, okay, let's remove tartaric acid altogether and start doing synthesis at 40 degrees. Same thing. So this is spontaneous symmetry breaking, right? Here you have a situation where without any chiral interference, you get almost, depending randomly on which experiment you do, you can get this symmetry breaking. So this was also a very interesting feature. Actually, the next PhD student, after Gal, she studied this further, and it turns out not to be completely spontaneous symmetry breaking. It's not completely random. We found out that, okay, we were doing it in small glass vessels, vials, like small cups. And we do it under steering with a magnetic steering bar that is coated with Teflon. So the glass cup, we just throw each time, it's like disposable. So we throw them away, but the magnetic steering bars are more expensive, so we keep them. It turns out that even if you clean the magnetic steering bar, which is Teflon coating, you clean the Teflon in very strong acids, boiling it. Still, you do one experiment with tartaric acid, you direct the whole system to the right, you clean the steering bar, you put it in a new experiment, it goes to the right. So tiny, tiny impurities of whatever is left inside pores in the Teflon and other materials, we used also glass coating on the magnetic steering bar, is enough. It's huge sensitivity, but not to the chiral molecules. If you take usually we take a lot of tartaric acid molecules to direct the system. If we take just a little, maybe 1% or 0.1% of the tartaric acid that we use for the full selection, no effect of tartaric acid. But if we take crystals, so preformed crystals, and we put just 1 millionth of the amount of crystals that we get in one synthesis and put it in a new synthesis, it will go to the right. So the slope here is basically infinite. So you have basically almost infinite chiral amplification. And this is what this means, okay? So we were talking actually to Chaim Diamant in our department, who is a theorist and a theoretician, and trying to model this. So, well, he actually pointed out that it looks like magnetic systems, and it looks like paramagnetic to ferromagnetic transition. And so he basically made a self-consistent field-based calculation, basically, just stating the fact that there will be a slightly different absorption energy of tartaric acid molecules that are left-handed or right-handed, or let's say on left-handed crystals, which is logical. And basically took some parameter. I mean, the trickiest part is to understand the symmetry breaking. So he just took a phenomenological parameter, basically based on Flory-Huggins theory for solutions of polymers, just to describe a correlation parameter that will give you the chiral amplification. Again, it's just phenomenological, and it's in the framework of statistical thermodynamics, assuming that thermodynamics really governs what's going on here, which is completely uncertain. But anyway, in describing like phase transition as a function of magnitude of this parameter, which changes as we go down in temperature. So phenomenologically, we could get it. Actually, later on, one of the reviewers, actually a friend of mine, told us about another guy that already used the term ferrochirality. So he already made the comparison or this analogous self-consistent Weiss model of ferromagnetism for chirality, but that was in helical polymers that spontaneously convert heterogeneous. So those straight lines are basically fits of Heinz model, which is described here basically the probability of getting some enantiomeric excess when you have some H value of the tartaric acid molecule. But this is surely just part of, it's one possibility, but it's just a model. We strongly believe that there are kinetic effects that are strongly affecting what is going on, especially in this what presumed secondary nucleation or whatever causes this very strong chiral amplification. So this is very recent results, for example, of measuring, following in situ the formation of the nanocrystals by looking at the europium emission. Europium does not emit when it's just dissolved in solution because the water molecules kills the emission of the europium. So only when it's embedded in the nanocrystals, it can emit light. So this is very convenient marker to follow the formation of the nanocrystals. So this is how they form, this is how it looks, the time dependence of formation of the nanocrystals. I won't go into this. This is really currently what we are studying. Sorry, previous slide.
Did you also look at the cycle? Is there any hysteresis?
Yeah, there's tiny hysteresis that can appear. This random symmetry breaking can even, reverse a very small excess, but I'm not sure. I mean, how far you can push, ferromagnetism, concepts to this. But yeah, there are like tiny hysteresis. So I just conclude. So we found an interesting system that knows how to break the symmetry completely and go all the way to the right or the left. Contrary to the sodium chloride previous experiment that you've seen, it does not ripen. Once this is very insoluble material once it's formed, so you cannot recycle it by continuous stirring. So it's a different way of symmetry breaking, which is all in probably in the nucleation stage of the nanocrystals. How do they decide to be right-handed or left-handed? As I saw, there's almost spontaneous symmetry breaking with huge sensitivity at low temperatures. When the formation of the nanocrystals is very slow, with almost infinite chiral amplification. What I mentioned earlier, a tiny breaking of the symmetry in very small numbers can lead to very high excess. So this lanthanide ion system is a very convenient system to study in crystal formation and all that. And there's still an issue of understanding how much thermodynamics and how much kinetics are responsible for the crystallization here. And even we think that it might be also interesting to test in the concept of models of breaking, spontaneous symmetry breaking, and the evolution of life. And so thank you for your attention.
We have time for a few questions here.
So if I understand, the message is that you want to polarize chirality, you need to use some other chiral.
Not necessarily. Actually, you can have almost like, it's like almost homeopathic, any tiny,
Be very weak, but somehow you need to break the symmetry. And how does nature do that? Where does the tartaric acid then? Where does it polarize?
Yes, so clearly, I mean, in nature, you didn't have one enantiomer of tartaric acid before there was life, of course. So there are huge number of models that can tell you how initial symmetry breaking would occur. But if you have such a high sensitivity, so maybe even a local random fluctuation could give you a local break of symmetry in some, scale. I don't know what is the scale. That's one possibility. The people, this is one of the models that people try to get. But other things, circularly polarized light from space that caused some photochemistry and broke the symmetry. I told you about the weak force that very difficult to understand how it would affect it.
I don't know anything about biology. If you take the world and split everything, the world would operate the same, like light.
Yeah, I see no reason why you couldn't have the reverse light, the mirror symmetry in other places. I mean, as far as we understand. Yeah, probably.
Yeah.
Is there a model that describes the interaction between molecules?
So yeah, people, there are lots of molecular dynamics type simulations where you can simulate how molecules, and I mean, people have studied this a lot. I mean, Meir Lav and Zerovich got many prizes for understanding how amino acid crystals form and how different interferences, for example, cause them, to...
I'm asking, is it possible to have some effective interaction model, like in Heisenberg model in magnets?
So yeah, sure. So what Chaim had in this model is we decided that, I think 1% energy out of the, it's difficult to simulate the interaction of a molecule with the surface of the terbium phosphate. We just assume that you have 1% of the total interaction energy difference, just 1% difference between L or D molecules interacting with, L surface. So, and this is actually probably the ballpark of number of differences that you would get. People tried, for example, to use quartz crystals have chiral surfaces also. So people try to understand the difference in energy of absorption of right and left-handed amino acid as a model, for example, for symmetry breaking in the evolution of proteins. So they are very tiny. But you can find ways to amplify this tiny difference, as in even the model said, you can get this amplification. Thermodynamic.
There are, I guess, two time scales involved. One, how often a nucleus is formed, and how once a nucleus is formed, how rapidly the crystal grows.
Yes.
Is there a clear separation between these two time scales?
Yes, so they are, okay, this belongs to the category of models of crystallization. So there's a classical nucleation and growth model called Lamer model, which indeed separates. It says that at certain supersaturation, you cross some threshold when you increase the concentration of your precursors, and you will get burst nucleation. Then the concentration will drop below this threshold, and then you cannot have any more nucleation and we'll have growth. So yeah, this is very relevant, of course. We have, from the kinetic measurements, we have clear evidence that it's this kind of model. We have a bank of nucleation and then slow growth. There are other models where you can have simultaneous nucleation and growth. We cannot say dramatic, that clearly you have stop of nucleation at some point. And especially this secondary nucleation is something nobody really, really observed directly. And this is what we are trying to do.
Okay, so we're out of time. Let's thank you again.
השאלה שלך, דינמיקה וקינטיקה, זה לא בכלל סותר.
לא, לא סותר.
לא הבנתי בדיוק מה אתה מתכוון פה. כי קינטיקה יכולה להוביל יותר מדינמיקה, אז אני רק אומר לך בתור צופה שזה קצת בגלל.
לא, בסדר, זו אמירה כזאת באמת היא מעובנת, אבל אפשר להגיד, האם השקירת סימטריה עצמה, היא מופיעה בראה קירלית הזאת, זה מופיע יותר קינטית או יותר תרמודינמית? המודל של חיים כאילו מראה כאילו תרמודינמית, אתה יכול לקבל את זה, אתה לא חייב קינטיקה, אני חושב שבמציאות, יש לי תחושה שהקינטיקה היא
לא, אבל במצב הסופי, התרמודינמיקה זה תמיד בזמנים ארוכים, שהמערכת בשיווי משקל, אם יש שיווי משקל, מגיע לזה, אז